We're about to embark on a journey that will take us far beyond the familiar boundaries of our solar system to meet some of the most mysterious and calming visitors our cosmic neighborhood has ever received. Tonight, we're exploring the gentle wanderers from the vast spaces between stars, the interstellar visitors that have crossed unimaginable distances to grace us with their presence. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and liking this video. It helps the algorithm find more curious minds like ours who find peace in contemplating the wonders of the universe. The visuals are here for you, but feel free to close your eyes, breathe deep, and let your imagination drift through the cosmic void alongside these ancient travelers. I'd love to know where you're listening from tonight. Feel free to comment your time and location below. You're standing in your garden on a quiet evening, watching the familiar dance of planets and stars. Everything you see belongs to our solar system, our cosmic home. But what if I told you that right now, as you gaze upward, there are objects moving through our neighborhood that don't belong here at all? Visitors from realms so distant that their journey to reach us has taken millions, perhaps billions of years. These are the interstellar objects, and their stories are among the most soothing and profound tales the universe has to offer. Welcome to this peaceful exploration of the cosmos beyond our solar system, where we'll discover why these mysterious visitors bring not fear or chaos, but a deep sense of calm and wonder about the gentle nature of our universe. We'll uncover the relaxing truths about how vast spaces between stars nurture these wandering objects, how they travel through the cosmic dark with serene patience, and why their very existence speaks to the beautiful, interconnected nature of our galaxy. The story begins in the spaces between stars, those vast regions of near-emptiness that stretch for light years in every direction. When we think of space, we often imagine the bustling activity of our solar system, with planets orbiting, comets swooping in elegant arcs, and asteroids tumbling through their predictable paths. But venture beyond the influence of our sun, and you enter a realm of profound tranquility. Here, in the interstellar medium, matter is so sparse that you could travel for millions of miles and encounter nothing more substantial than a few atoms of hydrogen drifting in the cosmic breeze. Yet this apparent emptiness is not truly empty. It's filled with a subtle presence, a gentle background of particles and fields that permeates the entire galaxy. Think of it as the universe's version of a calm, still pond. Occasionally, ripples disturb this serenity as massive stars are born or die, sending shockwaves through the interstellar medium. But for the most part, this cosmic space exists in a state of peaceful equilibrium, a vast reservoir of potential that has remained largely unchanged for billions of years. It's from these tranquil depths that our interstellar visitors emerge. These objects, freed from the gravitational embrace of any particular star, drift through the galaxy like cosmic nomads. They carry with them the history of distant stellar systems, the remnants of planetary formation processes that occurred when our own solar system was nothing more than a swirling disk of dust and gas. Some of these wanderers may have been traveling for longer than life has existed on Earth, making their way through the galaxy with the patience that only cosmic timescales can teach. The first confirmed interstellar visitor to our solar system arrived with all the subtlety of a whisper. In October 2017, astronomers detected an unusual object moving through the inner solar system. At first glance, it appeared to be just another asteroid or comet, the kind of rocky debris that regularly passes through our cosmic neighborhood. But as observations continued, something remarkable became clear. This object, which they named Oumuamua, was moving too fast and on a trajectory that could only mean one thing. It had come from beyond our solar system. Oumuamua's discovery was like receiving a postcard from a distant land we'd never visited. Here was tangible proof that the spaces between stars weren't empty wastelands, but highways traveled by objects carrying the stories of alien worlds. The very name Oumuamua, which means scout or messenger in Hawaiian, captures the peaceful nature of this first contact. This wasn't an invasion or a dramatic collision. It was simply a gentle visitor passing through, offering us a glimpse of the wider galaxy beyond our local cosmic bubble. What makes these interstellar visitors so profoundly calming is their unhurried nature. Oumuamua had been traveling through space for millions of years before it encountered our solar system. During that vast span of time, it experienced the ultimate in cosmic solitude, drifting through regions where the nearest star was merely a distant point of light. There's something deeply soothing about imagining this ancient object maintaining its course with absolute consistency, unaffected by the dramas of stellar birth and death, the formation and destruction of planetary systems, the rise and fall of countless civilizations that might have existed along its path. The journey of an interstellar object is the ultimate meditation on patience and persistence. These cosmic wanderers don't rush through space. They don't change course on a whim or deviate from their paths without cause. They simply exist in a state of perpetual motion, following the gentle curves of gravitational fields that extend across the galaxy like invisible highways. Their movement is so gradual that from our human perspective, they appear almost stationary, changing position by mere fractions of a degree over the course of months or years. This serene consistency extends to their physical properties as well. Unlike the objects in our solar system, which are constantly being reshaped by the sun's radiation, the solar wind, and gravitational interactions with planets, interstellar visitors have spent eons in the stable environment of deep space. They've been freeze-dried by the cosmic cold, preserved in a state that may be virtually identical to how they appeared when they first began their galactic journey. In a very real sense, these objects are time capsules, carrying pristine samples of matter from stellar systems that may no longer exist. The discovery of Oumuamua opened our eyes to a profound truth about the galaxy. We live in a vast recycling system where matter flows freely between stellar systems, carrying information and material across distances that dwarf human comprehension. Every star, every planet, every grain of cosmic dust is connected through this gentle exchange of matter and energy. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of these elements were once part of ancient stars that lived and died billions of years ago. Some of that stellar material may have spent millions of years drifting through interstellar space before eventually becoming incorporated into the cloud of gas and dust that formed our solar system. This cosmic recycling process operates on timescales that transform urgency into patience, anxiety into acceptance. When you realize that the atoms making up your body have been on a journey spanning billions of years, traveling through the hearts of stars, across the vast emptiness of interstellar space, and finally coming together in the precise arrangement that makes you possible. It's impossible not to feel a profound sense of peace about your place in the cosmic story. The second confirmed interstellar visitor provided even more reassurance about the gentle nature of these cosmic travelers. In August 2019, an amateur astronomer named Gennady Borisov spotted what initially appeared to be a faint comet in the constellation Draco. But as professional observatories turned their attention to this object, now called 2I Borisov, it became clear that this too was a visitor from beyond our solar system. Unlike the mysterious Oumuamua, which revealed few details about its composition and origin, Borisov was refreshingly familiar. It behaved exactly like the comets we know from our own solar system, developing a beautiful tail of gas and dust as it approached the Sun. Spectroscopic analysis revealed that its composition was remarkably similar to comets formed in our local neighborhood, suggesting that the processes of planetary formation are universal, creating similar types of objects regardless of which star system hosts them. This discovery was profoundly comforting because it suggested that the universe operates according to consistent principles. The same physical laws that govern the formation of comets in our solar system also apply in distant stellar neighborhoods. There's a beautiful uniformity to the cosmos, a reassuring predictability that extends across the vast distances between stars. When astronomers study objects like Borisov, they're not encountering alien phenomena that defy understanding. Instead, they're seeing familiar processes played out on a galactic stage, confirming that the universe is comprehensible and that the patterns we observe locally hold true on much larger scales. The gentle nature of these interstellar encounters becomes even more apparent when you consider the vast scales involved. Our solar system occupies a region of space roughly 100,000 astronomical units in diameter, where 1 astronomical unit is the distance from Earth to the Sun. That sounds enormous until you realize that the nearest star system, Alpha Centauri, is more than 250,000 times farther away. The spaces between stars are so vast that the probability of any particular interstellar object passing close enough to Earth for detailed study is vanishingly small. Yet here we are, having encountered not one, but at least 2 of these cosmic wanderers in just a few years of careful observation. This suggests that interstellar space is filled with far more objects than we previously imagined. A vast population of rocky fragments, icy comets, and perhaps even larger bodies drifting between the stars like seeds on a cosmic wind. The galaxy is not a collection of isolated stellar systems, but rather a connected ecosystem where material flows freely from one region to another, carried by these patient messengers that traverse the cosmic deep. The implications of this discovery extend far beyond astronomy. These interstellar visitors remind us that isolation is an illusion, that even the vastest distances can be bridged given sufficient time. They speak to the fundamental interconnectedness of all things in the universe, the way that matter and energy flow from one system to another across scales of space and time that dwarf human experience. In their unhurried journey across the galaxy, they embody a kind of cosmic wisdom about patience, persistence, and the value of the long view. As we continue our exploration of these gentle visitors from beyond the solar system, we'll discover even more reasons to find comfort in their presence. We'll learn about the peaceful processes that set them on their interstellar journeys, the serene environments they traverse, during their million-year voyages, and the subtle ways they influence and are influenced by the cosmic medium through which they travel. These are not harbingers of cosmic catastrophe, but rather ambassadors of the deep peace that pervades the universe between the stars. There's something almost meditative about the way these cosmic wanderers interact with the interstellar medium during their long journeys. As they drift through the galaxy, they encounter regions of space that exist in a state of profound equilibrium. The density of matter in these regions is so low that a teaspoon of interstellar space would contain fewer atoms than you could count on your fingers. Yet this sparse environment isn't empty. It's filled with the gentlest of cosmic breezes, streams of charged particles and magnetic fields that flow like invisible rivers between the stars. These interstellar currents move with the patience of geological processes, taking millions of years to shift and change direction. An interstellar visitor passing through these regions experiences forces so subtle they would be imperceptible to human senses. Yet over the vast timescales of galactic travel, these gentle influences can slowly alter an object's path, nudging it toward new destinations with the softest of touches. It's as if the galaxy itself is breathing, inhaling, and exhaling matter in slow, rhythmic cycles that span millions of years. The temperature in these interstellar regions hovers just a few degrees above absolute zero, creating an environment of perfect preservation. Any organic molecules that might have formed on these wandering objects remain frozen in time, protected from the harsh radiation and chemical reactions that would quickly break them down in more active environments. In this cosmic deep freeze, complex chemistry can persist for geological ages, carrying the molecular signatures of distant worlds across unimaginable distances. Consider for a moment the journey of a typical interstellar visitor. It begins its voyage perhaps 4 billion years ago, ejected from a young planetary system by the gravitational dance of forming planets. As it leaves the warm embrace of its parent star, it enters the vast twilight of interstellar space, where starlight is so dilute that high noon would appear darker than the deepest earthly night. Here, in this realm of perpetual dusk, our wanderer begins a journey that will outlast entire stellar generations. The first million years pass in silence. The object, perhaps a rocky fragment no larger than a city block, maintains its course with unwavering consistency. It encounters no obstacles, experiences no dramatic events, simply continues forward through the cosmic void with the persistence of a meditation bell that rings once and continues resonating for eons. The gentle radiation pressure from distant stars provides the only force acting upon it, so subtle that it takes centuries to produce any measurable change in velocity. As millennia turn into millions of years, the wanderer passes through different neighborhoods of the galaxy. It might drift through the outskirts of stellar nurseries, regions where new stars are being born from clouds of gas and dust. Even here, in these relatively active regions, the environment remains peaceful from the perspective of our tiny traveler. The stellar winds and radiation that seem so violent when viewed on astronomical scales are spread across such vast volumes of space that they register as the gentlest of caresses on any individual object. The magnetic fields that permeate interstellar space create invisible highways that guide charged particles along graceful curves spanning thousands of light years. These cosmic magnetic field lines act like the grooves in a vast record, directing the flow of matter and energy through the galaxy, in patterns of elegant complexity. Our interstellar visitor, if it carries any electric charge, will find its path gently influenced by these fields, guided along trajectories that connect distant regions of the galaxy in ways that reveal the hidden architecture of cosmic magnetism. During its long journey, the wanderer may encounter other travelers, fellow refugees from distant stellar systems, making their own patient way across the galactic disk. These meetings occur so rarely and at such vast distances that they're more like ships passing in the night than actual encounters. Two objects might pass within a few astronomical units of each other, closer than they've been to anything else for millions of years, yet still separated by distances that would take light hours or days to cross. There's something profoundly comforting about imagining these chance encounters in the cosmic deep. Two ancient wanderers, each carrying the stories of worlds that may no longer exist, sharing a moment of relative proximity before continuing on their separate paths. They exchange no information, create no disturbance, simply acknowledge each other's presence through the subtle gravitational influence they exert across the emptiness that separates them. The dust grains that populate interstellar space tell their own story of cosmic recycling and renewal. These microscopic particles, each smaller than the width of a human hair, are the remnants of stellar atmospheres, blown into space by stellar winds or scattered by supernova explosions. They drift through the galaxy like cosmic pollen, carrying the chemical signatures of their parent stars to distant regions, where they may eventually become incorporated into new solar systems. An interstellar visitor passing through these dust clouds experiences what might be described as a cosmic snowfall, so gentle that individual grain impacts occur perhaps once every few years. Each collision adds a microscopic layer to the wanderer's surface, building up a patina of interstellar dust that records the chemical composition of every region it has passed through. Over millions of years, this accumulation creates a detailed log of the object's journey, a geological record written in layers of cosmic dust. The radio signals that permeate interstellar space add another dimension to this peaceful environment. The galaxy is filled with a constant background hum of radio waves, generated by everything from spinning neutron stars to the remnant radiation from the Big Bang itself. This cosmic static creates a kind of interstellar music, a symphony of electromagnetic radiation that has been playing continuously for billions of years. Our wandering visitor moves through this radio environment like a silent listener, absorbing and reflecting these signals in ways that depend on its composition and surface properties. Pulsars, those rapidly spinning neutron stars that act as cosmic lighthouses, sweep beams of radio waves across the galaxy with clockwork precision. As an interstellar object passes through these beams, it experiences brief moments of illumination, bathed in radio waves that have traveled across thousands of light years to reach it. These encounters last for mere seconds or minutes, but they represent moments of connection across the vast distances that separate objects in the galaxy. The gravitational environment of interstellar space operates according to principles of exquisite subtlety. Far from any massive stars or planets, our wanderer experiences gravity as a gentle tide, the combined pull of billions of distant suns creating a gravitational field so smooth and gradual that it changes imperceptibly over the course of centuries. This environment allows objects to maintain nearly straight-line trajectories across vast distances, following paths that would appear perfectly linear to any observer traveling along with them. Yet even in this realm of gravitational calm, there are features that add interest to the cosmic landscape. The galaxy's spiral arms create regions of slightly enhanced stellar density, where the combined gravitational influence of many stars can gradually deflect the paths of passing objects. These deflections are so gentle that they occur over millions of years, slowly curving the trajectories of interstellar wanderers in ways that are barely perceptible, but ultimately significant. Dark matter, that mysterious substance that makes up the majority of the galaxy's mass, creates its own subtle gravitational influence on interstellar travelers. Though we cannot see or directly detect dark matter, its gravitational effects permeate the galaxy, creating a kind of invisible scaffolding that influences the motion of everything from individual particles to entire star clusters. Our wandering visitor moves through this dark matter environment like a boat on an invisible ocean. Guided by currents we're only beginning to understand, the cosmic microwave background radiation, that faint afterglow of the Big Bang itself, bathes all of interstellar space in a uniform glow of ancient light. This radiation has been cooling and redshifting for nearly 14 billion years, but it still carries enough energy to gently warm any object traveling through space. For an interstellar visitor, this cosmic background provides a constant, gentle source of heat, preventing it from cooling all the way down to absolute zero and maintaining it at a temperature just barely above the coldest possible state of matter. As we contemplate these gentle influences that shape the journey of interstellar visitors, we begin to understand that space between the stars is not an empty void, but rather a richly textured environment filled with subtle phenomena. These cosmic wanderers don't travel through nothingness. They navigate through a medium that's alive with magnetic fields, radiation, dust, and gravitational influences that combine to create a landscape of extraordinary beauty and complexity. The timescales involved in these journeys transform our understanding of patience and persistence. When we consider that an interstellar visitor might travel for longer than complex life has existed on Earth, we begin to appreciate the deep time perspective that governs cosmic processes. These objects embody a kind of temporal wisdom, a demonstration of what can be accomplished through steady, consistent motion maintained over unimaginable spans of time. This perspective offers us a profound lesson in cosmic patience. While human civilizations rise and fall in mere thousands of years, these interstellar messengers maintain their courses with unwavering dedication across millions of centuries. They've witnessed the galaxy evolve, seen entire regions of space transform as massive stars are born, live their brief but brilliant lives, and explode in supernovae that enrich the interstellar medium with heavy elements. Through all of these cosmic upheavals, our wandering visitors continue their journeys with serene indifference to the dramas unfolding around them. The way these objects respond to their environment reveals another source of deep tranquility. Unlike spacecraft or planets that must constantly adjust their trajectories to maintain stable orbits, interstellar visitors exist in a state of perfect equilibrium with their surroundings. They neither fight against the forces they encounter, nor frantically attempt to change direction. Instead, they accept whatever gentle influences they experience, allowing their paths to be subtly modified by the cosmic currents while maintaining their overall sense of direction and purpose. This acceptance extends to their interaction with stellar radiation as well. When an interstellar object passes relatively close to a star during its journey, it doesn't struggle against the increased heat and radiation pressure. Instead, it simply absorbs what energy it can use and reflects the rest, allowing the stellar wind to gradually alter its surface properties without resistance. Over time, this process creates a kind of cosmic patina, a weathered surface that tells the story of every star the object has encountered along its path. The rotation of these cosmic wanderers adds another layer of meditative beauty to their journeys. Many interstellar objects spin slowly as they travel, turning end over end with periods measured in hours or days. This gentle tumbling motion ensures that all surfaces of the object experience equal exposure to the cosmic environment, preventing any one side from becoming dramatically different from the others. It's as if these travelers are deliberately presenting every aspect of themselves to the universe, rotating slowly like prayer wheels in the cosmic wind. The chemical processes occurring on the surfaces of these objects unfold with the same patient rhythm that characterizes everything else about their journeys. Cosmic ray particles, high-energy radiation from distant sources, strike their surfaces and gradually alter their molecular composition. But these changes happen so slowly that individual chemical transformations might take thousands of years to complete. The surface chemistry of an interstellar visitor is like a book written in geological time, with each chapter requiring millennia to unfold. Some interstellar objects may carry water ice preserved from their original formation billions of years ago. This ice exists in a state of perfect hibernation, frozen so thoroughly that molecular motion has nearly ceased. Locked within these ancient crystals might be traces of organic compounds, complex molecules that formed in the primordial disk of their parent star system. These molecules wait patiently, preserved in cosmic amber, carrying information about the chemical conditions that existed when our galaxy was young. The magnetic properties of interstellar visitors reveal another aspect of their peaceful nature. Many of these objects likely contain metallic components that became magnetized during their formation or through exposure to stellar magnetic fields. As they travel through the galaxy's magnetic environment, they act like tiny compass needles, their magnetic fields aligning with the larger galactic magnetic structure. This creates a subtle form of navigation, allowing these objects to sense the invisible magnetic highways that crisscross our galaxy. The gravitational interactions between interstellar objects and the stellar systems they pass near provide some of the most beautiful examples of cosmic choreography. When a wandering visitor approaches a star system, it doesn't crash through like a bull in a china shop. Instead, it follows graceful curves dictated by gravitational physics, its path bending smoothly as it feels the star's influence. These encounters are like cosmic ballet performances, with the visitor executing perfect gravitational pirouettes before continuing on its way. Sometimes these gravitational encounters result in what astronomers call gravity assists, where the visitor gains or loses speed through its interaction with a star's gravitational field. But even these dramatic changes in velocity occur gradually over periods of months or years, as the object slowly spirals through the star's gravitational influence. There's nothing sudden or violent about these interactions, just the smooth operation of physical laws playing out on cosmic scales. The way interstellar visitors interact with planetary systems reveals the gentle nature of cosmic mechanics on an even finer scale. When Oumuamua passed through our solar system, it followed a hyperbolic trajectory that carried it safely past all of our planets without creating any disturbance. Its presence was so subtle that it required our most sensitive instruments to detect, and its influence on the solar system's dynamics was completely negligible. This is typical of interstellar encounters, which occur with such delicate precision that they rarely disturb the established order of stellar neighborhoods. The dust and gas that these objects shed as they travel through space becomes part of the interstellar medium itself, contributing to the cosmic recycling process that connects all parts of the galaxy. Tiny particles eroded from their surfaces by cosmic ray bombardment drift away into space, where they may eventually become incorporated into new stars and planets. In this way, interstellar visitors serve as cosmic seed distributors, spreading material from one stellar system to another across vast distances and timescales. The radio emissions from some interstellar objects provide a soundtrack to their cosmic journeys. As they tumble through space, variations in their shape and composition create subtle changes in how they reflect and emit radio waves. These signals are incredibly faint, detectable only by our most sensitive radio telescopes, but they add another dimension to our understanding of these cosmic wanderers. Each object broadcasts its own unique radio signature, a kind of cosmic identification card that encodes information about its composition, rotation, and history. The infrared radiation emitted by interstellar visitors tells the story of their thermal history. Objects that have spent millions of years in the deep cold of interstellar space emit heat at wavelengths that reveal their internal temperature structure. This thermal radiation provides clues about their composition and internal properties, allowing astronomers to peer inside these cosmic time capsules without ever physically touching them. The way these objects interact with cosmic dust provides another window into their peaceful nature. As they travel through regions of space containing microscopic particles, they experience a constant, gentle bombardment of dust grains. Each impact is incredibly small, but over millions of years, this cosmic sandblasting gradually erodes their surfaces, rounding sharp edges and creating smooth, weathered textures. The process is so gradual that it would be imperceptible to human observers, yet it demonstrates the patient way that cosmic forces reshape matter over geological time. The electrical properties of interstellar visitors change slowly as they journey through regions of space with different charge densities. In some areas, they might accumulate a slight positive charge as electrons are stripped away by cosmic radiation. In others, they might collect electrons and become negatively charged. These electrical variations create subtle differences in how the objects interact with magnetic fields and charged particles, adding another layer of complexity to their cosmic journeys. The spectroscopic signatures of these objects reveal the elements they contain, providing direct evidence of the stellar nucleosynthesis processes that created their constituent atoms. When astronomers analyze the light reflected from interstellar visitors, they're essentially reading the periodic table written in starlight, identifying elements that were forged in the cores of ancient stars and distributed through the galaxy by stellar winds and supernova explosions. The orbital mechanics governing the motion of interstellar visitors demonstrate the elegant simplicity of gravitational physics operating on cosmic scales. These objects follow trajectories that can be precisely calculated using the same mathematical principles that govern the motion of planets and comets. Yet their paths extend across such vast distances that they connect regions of space that have never been linked by any other form of matter or energy. The discovery techniques used to find these cosmic wanderers reveal how they blend seamlessly into the background population of solar system objects. They're identified not through any dramatic signatures or unusual properties, but through careful analysis of their orbital characteristics. This subtlety speaks to their gentle nature, the way they visit our cosmic neighborhood without fanfare or disturbance, like polite guests who arrive quietly and leave without disturbing anything. The follow-up observations of confirmed interstellar visitors provide ongoing lessons in cosmic patience. These objects move so slowly across the sky that tracking their motion requires observations spanning months or years. Astronomers must wait patiently for these cosmic messengers to reveal their secrets, learning to appreciate the slow rhythm of interstellar travel and the deep time perspective it represents. As we reflect on these gentle visitors from beyond our solar system, we begin to understand that they represent something profoundly comforting about the nature of our galaxy. They demonstrate that the cosmos operates according to principles of patience, persistence, and peaceful coexistence. In their unhurried journeys across the vast spaces between stars, they embody a kind of cosmic wisdom that speaks to the fundamental tranquility underlying all of existence. The gravitational signatures left by these interstellar wanderers create ripples in the fabric of space-time so subtle they're barely detectable even by our most sensitive instruments. Yet these gentle distortions in reality itself tell a story of cosmic connectivity that spans the entire galaxy. Each visitor carries with it the gravitational memory of every massive object it has encountered during its million-year journey, creating a kind of cosmic fingerprint that encodes the structure of distant stellar neighborhoods. When we study the way these objects bend and flex under the gentle tidal forces they experience during their travels, we discover that they're not rigid, unchanging lumps of rock and ice. Instead, they're dynamic entities that respond to their environment with fluid grace. The microscopic stresses created by temperature variations and tidal forces cause them to expand and contract in slow, rhythmic cycles that mirror the breathing of some vast cosmic organism. The organic compounds that may exist on the surfaces of these visitors represent some of the most ancient chemistry in the galaxy. These molecules, if they exist, have been preserved in pristine condition by the perfect vacuum and extreme cold of interstellar space. They carry within their molecular bonds the chemical signature of stellar atmospheres from billions of years ago, when the galaxy was young and the first generation of carbon-rich stars was beginning to seed space with the building blocks of complexity. The way these interstellar messengers interact with solar wind creates some of the most delicate phenomena in our solar system. As they pass through the sun's sphere of influence, the charged particles streaming outward from our star encounter the magnetic fields and surface materials of these visitors, creating subtle auroras and electromagnetic disturbances so faint they require space-based instruments to detect. These interactions are like whispered conversations between our local star and these ancient wanderers, exchanged in the language of plasma physics and electromagnetic fields. The crystalline structures within these objects tell stories of formation processes that occurred in stellar neighborhoods so distant we may never directly observe them. The way atoms are arranged within their rocky matrices reflects the temperature and pressure conditions that existed during their birth, creating a kind of cosmic archaeology that allows us to study the planetary formation processes of alien solar systems. Each crystal grain is a library containing information about stellar winds, nebula chemistry, and gravitational dynamics from regions of space we can only dream of visiting. The isotopic ratios found in materials ejected from these visitors provide direct evidence of the nuclear processes that powered their parent stars. Different stellar masses and metallicities create distinct isotopic signatures in the elements they produce, and these signatures remain preserved in the solid materials that eventually become interstellar wanderers. By analyzing these ratios, astronomers can determine not just where these objects came from, but when they began their journeys and what types of stars dominated their birth neighborhoods. The way these cosmic travelers interact with the solar system's gravitational environment reveals the exquisite precision with which celestial mechanics operates on interstellar scales. Their trajectories bend and curve as they pass through our neighborhood, but these changes occur with mathematical predictability that demonstrates the underlying order governing all cosmic motion. There's something deeply reassuring about watching these visitors follow paths that can be calculated with perfect accuracy, their future positions known with certainty years in advance. The thermal properties of interstellar objects provide insights into the energy balance that governs their long journeys through space. They exist in a state of perfect thermal equilibrium with their environment, absorbing exactly as much energy as they radiate away. This balance has been maintained for millions of years, creating objects whose internal temperatures reflect the average cosmic background temperature, modified only by the gentle warming effect of occasional stellar encounters. The magnetic field measurements taken as these objects pass through our solar system reveal the complex electromagnetic environment they've traveled through during their galactic odyssey. Their magnetic properties change slowly over time as they're exposed to different stellar magnetic fields and interstellar magnetic structures. These changes occur so gradually that they provide a kind of magnetic memory, recording the electromagnetic history of their journey across the galaxy. The way cosmic rays interact with the surfaces of these wanderers creates a continuous process of space weathering that operates on timescales measured in millions of years. High-energy particles from distant stellar explosions strike their surfaces and gradually alter their chemical composition, creating new compounds that exist nowhere else in the universe. This process transforms the outer layers of these objects into unique materials that represent a blend of their original composition and the cosmic ray environment they've encountered during their travels. The gravitational perturbations these visitors experience as they pass near massive objects during their journey create subtle changes in their rotation rates and orientational alignment. These changes accumulate over millions of years, causing the objects to tumble through space in complex patterns that encode information about every significant gravitational encounter they've experienced. Their current spin states are like fossil records of gravitational interactions spanning geological time. The way these objects fragment and shed material during their journeys contributes to the continuous mixing of matter throughout the galaxy. Tiny pieces broken off by micrometeorite impacts or thermal stress become independent travelers, carrying genetic samples of their parent objects to new regions of space. This process creates a vast network of material exchange that connects every corner of the galaxy through the patient circulation of cosmic debris. The spectral evolution of these wanderers as they age provides a window into the long-term effects of space exposure on different types of materials. Organic compounds undergo slow chemical changes when exposed to cosmic radiation, creating new molecular species that may not exist anywhere else in the universe. These space-weathered surfaces develop unique optical properties that tell the story of millions of years spent bathed in the gentle radiation of distant stars. The way these visitors respond to the varying density of the interstellar medium they pass through reveals the subtle structure of galactic space. As they travel through regions of different particle density, they experience varying amounts of drag and heating, creating thermal cycles that span thousands of years. These long-period variations in temperature cause the objects to expand and contract in slow rhythms that mirror the large-scale structure of the galaxy itself. The acoustic properties of these objects, measurable through the way they ring when struck by micrometeorites, provide insights into their internal structure and composition. Like cosmic tuning forks, they vibrate at frequencies that depend on their size, shape, and material properties. These vibrations propagate through their solid matrices at the speed of sound, creating standing wave patterns that reveal hidden details about their internal architecture. The way these wanderers interact with the galactic halo, that vast spherical region of dark matter and sparse gas that surrounds our galaxy, demonstrates their role as probes of the most mysterious components of cosmic structure. As they travel through regions dominated by dark matter, their trajectories are subtly influenced by gravitational fields we cannot directly observe. Their paths serve as tracers of invisible matter, revealing the hidden scaffolding that holds galaxies together. The chemical gradients that develop within these objects over millions of years of space exposure create layered structures that record the history of their cosmic environment. Elements migrate slowly through their solid matrices in response to temperature variations and radiation exposure, creating concentration profiles that reflect the changing conditions they've encountered during their interstellar journey. These chemical archaeology records provide unprecedented insights into the evolution of galactic chemistry over cosmic time. The way these visitors interact with the heliosphere, that vast bubble of solar wind that surrounds our solar system, creates boundary phenomena that reveal the dynamic interface between stellar and interstellar environments. As they cross from interstellar space into our solar neighborhood, they experience a gradual transition from the galactic cosmic ray environment to the solar particle environment, creating measurable changes in their surface chemistry and electromagnetic properties. The orbital resonances that occasionally develop between these wanderers and objects in our solar system create temporary gravitational relationships that can last for thousands of years. During these periods of resonant interaction, the visitors become temporary members of our cosmic family, sharing orbital characteristics with planets or asteroids while maintaining their ultimate destiny to return to interstellar space. The way these objects serve as natural laboratories for studying matter under extreme conditions provides insights into fundamental physics that cannot be replicated in earthbound experiments. They've been subjected to millions of years of cosmic ray bombardment, extreme temperature cycles, and the unique chemical environment of interstellar space, creating materials with properties that challenge our understanding of solid-state physics and chemistry. The magnetic field interactions between these visitors and planetary magnetospheres create subtle but detectable electromagnetic phenomena that reveal the complex electrical nature of solar system dynamics. As they pass through the magnetic fields of planets, they generate weak electric currents and create disturbances in the local space weather that can be measured by sensitive spacecraft instruments. The way these cosmic messengers carry information about the galactic chemical evolution demonstrates their role as libraries of stellar nucleosynthesis. The heavy elements they contain were created in the cores of massive stars that lived and died billions of years ago, and their isotopic compositions provide direct evidence of the nuclear processes that have enriched the galaxy with the elements necessary for planet formation and life. The gravitational lensing effects created by the most massive interstellar visitors, though incredibly subtle, provide opportunities to study the distribution of matter on scales much smaller than previously possible. Their gravitational fields act as natural telescopes, slightly magnifying the light from background stars and revealing details about stellar structure that would otherwise be unobservable. The way these objects influence the local interstellar medium as they pass through it creates bow shocks and wake structures that persist long after they've moved on. These disturbances in the cosmic plasma propagate outward at the speed of sound in the interstellar medium, carrying information about the passage of these visitors to regions of space they will never directly encounter. The thermal inertia of these wanderers, their resistance to temperature changes, reflects millions of years of thermal conditioning in the stable environment of deep space. They've achieved a state of perfect thermal equilibrium that makes them incredibly sensitive thermometers for measuring the temperature of the cosmic microwave background radiation and other subtle heat sources in interstellar space. The way these visitors serve as time capsules from the early galaxy provides direct access to materials that formed when the universe was much younger and had a very different chemical composition. They carry within their solid matrices samples of dust and gas that condensed from stellar winds when the galaxy contained far fewer heavy elements, offering glimpses into cosmic conditions that existed billions of years before Earth formed. As we contemplate the profound implications of these gentle visitors from beyond our solar system, we begin to understand that they represent something far more significant than mere curiosities or astronomical oddities. They are living proof of the interconnected nature of our galaxy, physical evidence that the spaces between stars are not empty barriers, but rather highways that connect every stellar system in a vast network of material and energy exchange. Their presence in our cosmic neighborhood serves as a gentle reminder that we are not isolated inhabitants of a single star system, but rather citizens of a galaxy-wide community where matter, energy, and perhaps even life itself flow freely between stellar homes. The patience they demonstrate in their million-year journeys teaches us about the deep time perspective that governs cosmic evolution, showing us that the most profound changes in the universe occur not through violent catastrophes, but through the accumulation of countless small, gentle processes operating over unimaginable spans of time. These interstellar wanderers embody the fundamental tranquility that underlies all cosmic processes. In their unhurried passage through our solar system, they demonstrate that the universe operates according to principles of harmony and balance, where even the most dramatic encounters unfold with graceful precision. They show us that the cosmos is not a chaotic battleground of competing forces, but rather a symphony of gravitational interactions, electromagnetic phenomena, and chemical processes all working together in perfect coordination. The very fact that we've been privileged to observe these cosmic messengers during their brief passage through our neighborhood fills us with a profound sense of connection to the larger galactic community. We are witnessing history in the making, observing objects that have traveled farther and seen more of the galaxy than any human-made spacecraft will ever achieve. Their stories span geological time and galactic distances, yet they pass through our cosmic backyard with such gentle grace that they disturb nothing and leave everything exactly as they found it. In studying these interstellar visitors, we learn not just about the objects themselves, but about our own place in the cosmic story. We discover that the elements in our bodies, the materials that make up our planet, and the energy that powers our sun are all part of the same galactic recycling system that these wanderers represent. We are not separate from these cosmic processes, but integral participants in the ongoing exchange of matter and energy that connects every part of our galaxy. The serenity these objects display in their cosmic journeys offers us a model for understanding patience, persistence, and the value of maintaining course even when the destination is uncertain, and the journey spans timescales beyond human comprehension. They teach us that the most meaningful accomplishments often require not dramatic action, but steady, consistent progress, maintained over vast periods of time. As we continue to discover more of these interstellar visitors in the years to come, each one will add new chapters to our understanding of the galactic ecosystem we inhabit. They will bring us samples of distant worlds, stories of stellar neighborhoods we can only imagine, and evidence of the cosmic processes that have shaped our galaxy over billions of years. Each visitor will be a gift from the deep space between stars, a gentle reminder that we are part of something far larger and more magnificent than our single solar system. The gravitational choreography these visitors perform as they navigate through dense stellar regions reveals the exquisite mathematical beauty underlying all cosmic motion. When an interstellar wanderer approaches a binary star system, it doesn't simply barrel through in a straight line. Instead, it executes a complex gravitational dance, its trajectory weaving between the two stars in curves that follow the elegant equations of celestial mechanics. These encounters can last for decades, with the visitor slowly spiraling through the combined gravitational field of both stars before emerging on the other side with a subtly altered course and velocity. The way these cosmic travelers respond to the galactic tide provides another window into the serene forces that shape their journeys. Our galaxy rotates like a vast pinwheel, and this rotation creates tidal forces that stretch and compress objects moving through different regions of galactic space. An interstellar visitor experiences these tides as gentle stretches and compressions that occur over millions of years, so gradually that the forces involved would be imperceptible to human senses, yet profound enough to slowly reshape the object's internal structure. The plasma interactions these wanderers experience as they pass through different regions of ionized gas create some of the most subtle phenomena in all of astrophysics. When charged particles in the interstellar medium encounter the magnetic fields carried by these objects, they create microscopic electrical currents that flow around the visitor like rivers of electricity. These currents are so faint that they would barely register on our most sensitive instruments, yet they represent a continuous dialogue between the wanderer and the electromagnetic environment it travels through. The way these objects accumulate cosmic dust during their journeys creates layered surfaces that tell detailed stories of galactic geography. Different regions of the galaxy contain dust with distinct chemical signatures, reflecting the types of stars and stellar processes that dominate each neighborhood. As an interstellar visitor travels through these regions, it accumulates dust layers like geological strata, building up a surface record that maps the chemical evolution of every galactic region it has encountered over millions of years. The resonant frequencies at which these objects vibrate when struck by micrometeorites reveal their internal structure with surprising precision. Like cosmic bells, they ring at specific pitches determined by their size, shape, and composition. These acoustic signatures change slowly over time as space weathering alters their surface properties and internal heating from radioactive decay modifies their density distribution. The result is a kind of cosmic symphony, with each visitor contributing its own unique tone to the music of interstellar space. The way these wanderers interact with the cosmic web, that vast network of dark matter filaments that connects galaxy clusters across the universe, demonstrates their role as tracers of the largest structures in existence. As they travel along these invisible highways of dark matter, their trajectories are subtly influenced by gravitational fields that extend across hundreds of millions of light years. Their paths serve as maps of this hidden architecture, revealing the skeletal framework upon which all visible matter in the universe is built. The thermal cycles these objects experience as they pass through regions of varying stellar density create slow rhythms of expansion and contraction that span thousands of years. In dense stellar neighborhoods, the combined radiation from many nearby stars gently warms them, causing their materials to expand slightly. As they move into the sparse regions between spiral arms, they cool and contract, creating thermal breathing patterns that mirror the large-scale structure of the galaxy itself. The way these visitors shed microscopic particles as they travel creates trails of material so diffuse they're almost impossible to detect. Yet these particle streams connect distant regions of the galaxy in ways that reveal the hidden circulation patterns of interstellar matter. Each wanderer leaves behind a breadcrumb trail of dust and molecular fragments that can be traced by sensitive instruments, providing maps of galactic air currents that operate on scales of space and time beyond human imagination. The chemical weathering these objects undergo during their cosmic journeys creates new compounds that exist nowhere else in the universe. The unique combination of cosmic ray bombardment, extreme temperature variations, and the pristine vacuum of interstellar space produces chemical reactions that cannot be replicated in any Earthbound laboratory. These space-weathered surfaces develop patinas of exotic materials that represent millions of years of slow chemistry operating under conditions of perfect isolation. The way these wanderers interact with stellar corona during close approaches to stars creates brief moments of intense electromagnetic activity that illuminate their surfaces with auroras invisible to human eyes, but detectable by specialized instruments. As they pass through the extended atmospheres of massive stars, they become temporary comets, developing faint tails of ionized material that stream behind them like cosmic prayer flags fluttering in the stellar wind. The gravitational memory these objects carry within their rotation states encodes information about every massive object they've encountered during their galactic odyssey. Their current spin patterns are fossil records of gravitational interactions, preserving the signatures of close encounters with black holes, neutron stars, and other exotic object stars, and massive planets in stellar systems whose light may never reach us. Each tumble and wobble tells a story of gravitational conversations that occurred millions of years ago in distant corners of the galaxy. The way these visitors serve as natural particle detectors reveals the hidden radiation environment of interstellar space. High-energy cosmic rays striking their surfaces create cascades of secondary particles that penetrate deep into their interiors, leaving tracks and radiation damage that accumulate over millions of years. These damage patterns provide a detailed record of the cosmic ray flux in different regions of the galaxy, creating natural dosimeters that measure the radiation climate of interstellar space. The magnetic field lines frozen into these objects during their formation preserve snapshots of the magnetic environments that existed in their birth stellar systems billions of years ago. As they travel through the galaxy's magnetic field, these fossil magnetic fields interact with the galactic magnetic structure, creating subtle torques that slowly alter their orientation over cosmic timescales. The result is a kind of magnetic archaeology that reveals the evolution of galactic magnetism over billions of years. The way these cosmic messengers interact with the galactic fountain, that slow circulation of gas between the galactic disk and halo, demonstrates their role as tracers of the galaxy's breathing patterns. As hot gas rises from star-forming regions in the disk and cool gas falls back down from the halo, these wanderers serve as passive markers that reveal the three-dimensional structure of these vast circulation cells that operate over hundreds of millions of years. The isotopic evolution that occurs within these objects as they age provides insights into fundamental nuclear processes operating under conditions that exist nowhere else in the universe. Radioactive elements within their matrices decay with half-lives measured in millions or billions of years, creating daughter isotopes at rates determined by the cosmic ray flux and temperature history they have experienced during their interstellar journey. These natural nuclear clocks provide precise dating methods that reveal the ages of stellar systems that may no longer exist. The way these visitors respond to the pressure waves that propagate through the interstellar medium reveals the acoustic properties of galactic space itself. Shock waves from supernova explosions create compression waves that travel through the sparse gas between stars at speeds of hundreds of kilometers per second. When these waves encounter an interstellar wanderer, they create tiny but measurable accelerations that alter the object's trajectory in ways that can be detected by careful positional measurements spanning decades. The surface chemistry evolution of these objects creates natural laboratories for studying how complex molecules behave under the extreme conditions of deep space. Organic compounds that may have formed in the atmospheres of their parent stars undergo slow transformations when exposed to cosmic radiation and the pristine vacuum of interstellar space. These reactions proceed at rates so slow that individual molecular changes might take centuries to complete, creating chemical processes that operate on timescales unknown in terrestrial chemistry. The way these wanderers interact with the local bubble, that region of hot, low-density gas that surrounds our solar system, provides insights into the recent history of stellar explosions in our galactic neighborhood. Our solar system exists within a cavity blown out by ancient supernova explosions. and the properties of interstellar visitors as they enter this region reveal the boundary conditions between the hot bubble interior and the cooler, denser interstellar medium beyond. The gravitational focusing effects these objects experience as they pass through the gravitational fields of massive stellar remnants create temporary magnification events that can reveal details about their internal structure. When a wanderer passes almost directly behind a neutron star or black hole as seen from Earth, the intense gravitational field acts as a natural telescope, slightly magnifying the visitor's reflected light and revealing surface features that would otherwise be invisible. The way these cosmic travelers contribute to the galactic chemical evolution demonstrates their role as mixing agents in the slow process that distributes elements throughout the galaxy. They carry samples of stellar nucleosynthesis products from one region of the galaxy to another, contributing to the gradual homogenization of chemical abundances that has occurred over billions of years of galactic evolution. Each visitor is a tiny but significant agent in the vast recycling system that ensures the galaxy's chemical heritage is shared among all its stellar citizens. The electromagnetic signatures these objects emit as they tumble through space create unique radio fingerprints that can be detected by sensitive arrays of radio telescopes. These signals are incredibly weak, often requiring observations spanning months or years to accumulate enough data for analysis, but they provide direct measurements of the object's rotation rates, surface composition, and internal structure. Each visitor broadcasts its own cosmic identification code, a radio signature as unique as a fingerprint. The way these wanderers interact with planetary magnetospheres during their passage through stellar systems creates brief but detectable disturbances in the local space weather. As they pass through the magnetic field boundaries that surround planets, they generate weak electric currents and create ripples in the charged particle environment that can be measured by spacecraft instruments. These interactions provide natural experiments in magnetospheric physics, revealing how small objects influence large-scale electromagnetic structures. The thermal conductivity measurements possible during the brief heating events these objects experience when passing close to stars reveal their internal structure and composition with remarkable precision. The way heat propagates through their interiors depends on their porosity, mineral composition, and internal fracture patterns, all of which can be inferred from careful observations of their thermal response to stellar heating. These natural thermal experiments provide insights into the internal architecture of objects that formed in alien stellar systems billions of years ago. The way these visitors serve as natural seismographs for detecting gravitational waves reveals their potential as components of galaxy-wide gravitational wave detection networks. The incredibly subtle stretching and compressing of space caused by gravitational waves from merging black holes and neutron stars creates tiny changes in the distances between these wandering objects. While these effects are far too small to measure with current technology, future advances might allow us to use interstellar visitors as nodes in a gravitational wave detector spanning the entire galaxy. The chemical gradients that develop within these objects over millions of years of cosmic ray exposure create internal structures that mirror the layered architecture of planetary atmospheres. Heavy elements tend to migrate toward their centers under the influence of radiation pressure, while lighter elements accumulate near their surfaces. This slow gravitational differentiation creates onion-like structures that preserve information about the radiation environment they've encountered during different phases of their galactic journey. The way these cosmic messengers interact with the streaming motions of gas in spiral density waves demonstrates their role as tracers of galactic dynamics on the largest scales. As they move through regions where spiral arms compress the interstellar medium, they experience subtle changes in the drag forces exerted by the enhanced gas density. These interactions create measurable perturbations in their trajectories that reveal the three-dimensional structure and motion of the galaxy's spiral pattern. The acoustic emissions these objects produce as they flex and crack under thermal stress create a kind of cosmic music that tells the story of their physical evolution. Temperature changes during stellar encounters cause their materials to expand and contract, creating mechanical stresses that are relieved through the formation of tiny fractures. Each crack produces acoustic waves that propagate through the object's interior, creating seismic events so gentle they would be imperceptible to human senses, but detectable by sufficiently sensitive instruments. The way these wanderers preserve records of the cosmic ray environment they've encountered provides insights into the history of stellar explosions throughout the galaxy. Different types of cosmic rays are produced by different astrophysical sources, and the radiation damage patterns accumulated in these objects' interiors create detailed maps of the supernova activity, pulsar emissions, and other high-energy phenomena they've encountered during their million-year journeys through galactic space. The electromagnetic induction effects created as these objects move through the galaxy's magnetic field generate weak electric currents that flow in complex patterns through their conductive materials. These currents create their own magnetic fields, which interact with the galactic magnetic structure to produce subtle torques that influence the object's rotation rates and orientational alignment. Over millions of years, these electromagnetic interactions can dramatically alter the spin states of interstellar wanderers. The way these visitors interact with the cosmic neutrino background reveals their potential as natural neutrino detectors spanning galactic distances. Neutrinos from distant stellar explosions, black hole formation events, and other high-energy astrophysical phenomena pass through these objects at rates that depend on their internal structure and composition. While individual neutrino interactions are incredibly rare, the accumulated effects over millions of years might create detectable changes in their internal chemistry. The crystallographic evolution that occurs within the solid materials of these wanderers provides insights into how matter behaves under the unique conditions of interstellar space. The combination of cosmic ray bombardment, thermal cycling, and mechanical stress from tidal forces creates slow changes in crystal structure that cannot be replicated in terrestrial laboratories. These changes occur so gradually that they preserve detailed records of the physical conditions these objects have experienced throughout their cosmic journeys. The way these objects serve as natural experiments in materials, science reveals how different substances respond to millions of years of exposure to the space environment. Metals become work-hardened by micrometeorite impacts. Organic compounds undergo slow polymerization reactions, and crystalline materials develop unique defect structures that record their radiation exposure history. Each visitor carries within its structure a library of materials, science data spanning geological timescales. The gravitational perturbations these wanderers create as they pass through stellar systems provide opportunities to study the distribution of mass on scales much smaller than previously possible. Their gravitational influence on planets, asteroids, and comets can be measured with extraordinary precision using modern astrometric techniques, revealing details about the internal structure and mass distribution of objects throughout the solar systems they visit. As we reflect on these countless gentle interactions that characterize the journeys of interstellar visitors, we begin to appreciate the profound interconnectedness that defines our galactic home. These cosmic wanderers are not isolated objects drifting aimlessly through empty space, but rather integral participants in a vast network of physical processes that connect every corner of the galaxy. They serve as ambassadors between stellar systems, carrying information and material across distances that would otherwise remain forever isolated from one another. Their presence in our cosmic neighborhood reminds us that we live in a dynamic, evolving galaxy where matter and energy flow freely between stellar homes. The gentle nature of their passage through our solar system demonstrates that the universe operates according to principles of harmony and balance, where even the most dramatic cosmic encounters unfold with mathematical precision and elegant grace. They show us that the cosmos is not a realm of chaos and destruction, but rather a symphony of gravitational interactions, electromagnetic phenomena, and chemical processes all working together in perfect coordination. The patient timescales on which these objects operate teach us about the deep time perspective that governs cosmic evolution. Their million-year journeys span periods so vast that entire stellar generations are born, live, and die during their passage between neighboring star systems. Yet they maintain their courses with unwavering consistency, embodying a kind of cosmic perseverance that speaks to the fundamental stability underlying all natural processes. In studying these interstellar messengers, we discover that the spaces between stars are not empty voids, but richly textured environments filled with subtle phenomena that operate on scales of space and time beyond human experience. The gentle forces that guide these wanderers through their galactic odysseys reveal the hidden architecture of cosmic structure. From the magnetic highways that crisscross interstellar space to the gravitational scaffolding of dark matter that holds galaxies together, these visitors remind us that we are not separate from the cosmic processes we observe, but integral participants in the ongoing story of galactic evolution. The elements in our bodies, the materials that make up our planet, and the energy that powers our sun are all part of the same vast recycling system that these wanderers represent. We are connected to every corner of the galaxy through the patient circulation of matter and energy that has been operating for billions of years, long before Earth formed and long before life began its remarkable journey toward consciousness. The serenity these objects display in their cosmic travels offers us a profound model for understanding patience, persistence, and the value of maintaining purpose, even when the journey spans timescales beyond imagination. They teach us that the most meaningful accomplishments often require not dramatic action, but steady, consistent progress maintained over vast periods of time. In their unhurried passage through our solar system, they demonstrate that true wisdom lies not in rushing toward distant goals, but in maintaining course with quiet confidence, trusting in the fundamental processes that guide all cosmic evolution. As we continue to discover and study more of these interstellar visitors in the years ahead, each one will bring us new insights into the nature of our galactic community. They will carry samples of distant worlds, stories of stellar neighborhoods we can only imagine, and evidence of cosmic processes that have shaped our galaxy over billions of years. Each visitor will be a gentle gift from the deep spaces between stars, a quiet reminder that we are part of something far larger and more magnificent than our single solar system. Participants in a cosmic dance that connects every atom in the universe through the patient rhythms of space and time. The way these cosmic wanderers create subtle gravitational harmonics as they move through regions of varying stellar density reveals another layer of the profound music that governs galactic dynamics. When an interstellar visitor travels through a dense star cluster, it experiences the combined gravitational pull of hundreds or thousands of stellar objects, each contributing its own gentle influence to the wanderer's trajectory. These individual gravitational voices blend together to create complex harmonic patterns that guide the object along paths of extraordinary mathematical beauty, trajectories that curve and spiral according to equations so elegant they seem almost alive. The resonance patterns that develop between these visitors and the rotating structure of our galaxy demonstrate the deep rhythmic connections that unite all cosmic motion. As they move through the galaxy's spiral arms, they encounter periodic variations in gravitational field strength that occur at frequencies determined by the galaxy's rotation period. Over millions of years, these regular variations can lock their orbital motions into resonant relationships with the galactic structure itself, creating stable pathways that persist for geological ages. The way these objects respond to the gentle pressure of starlight reveals another dimension of their peaceful interaction with the cosmos. Radiation pressure from distant stars creates forces so subtle they would be undetectable to human senses. Yet over the vast timescales of interstellar travel, these photon breezes can gradually alter the spin rates and orientations of wandering visitors. The accumulated effect of billions of photon impacts creates a kind of optical navigation system that slowly aligns these objects with the radiation fields of the galaxy. The crystalline memory effects that occur within the solid materials of these wanderers provide natural archives of the electromagnetic environments they've encountered during their cosmic journeys. Certain minerals can trap electrons in crystal defects when exposed to radiation, creating charge distributions that remain stable for millions of years. These trapped charges serve as natural dosimeters, recording the intensity and spectrum of cosmic radiation in different regions of galactic space, with a precision that rivals our most sophisticated instruments. The way these visitors interact with the slow tidal breathing of galactic rotation creates long-period variations in their trajectories that mirror the grand-scale motions of stellar populations. As our galaxy rotates, different regions experience subtle changes in gravitational field strength that occur over periods of hundreds of millions of years. Interstellar wanderers traveling through these regions experience corresponding changes in their orbital energies, creating slow oscillations in their paths that reflect the deep rhythmic patterns governing galactic evolution. The thermal equilibrium these objects maintain with the cosmic microwave background radiation demonstrates their exquisite sensitivity to the fundamental temperature of the universe itself. Having spent millions of years in the perfect thermal isolation of interstellar space, they've cooled to within a few degrees of absolute zero, achieving a state of thermal purity that makes them natural thermometers for measuring the temperature of the cosmic background radiation with extraordinary precision. The way these cosmic messengers preserve samples of pristine interstellar dust within their surface layers creates opportunities to study the raw materials of star formation in their most unprocessed state. Unlike the dust grains found in our solar system, which have been altered by billions of years of solar radiation and planetary gravitational influences, The dust accumulated by interstellar visitors represents direct samples of the interstellar medium in its natural condition, providing insights into the chemical composition of the galaxy before it was modified by stellar processing. The magnetic field interactions these wanderers experience as they cross the boundaries between different regions of galactic magnetic structure create subtle electromagnetic phenomena that reveal the hidden organization of cosmic magnetism. The galaxy's magnetic field is not uniform, but consists of distinct domains with different orientations and strengths, separated by boundary layers where the field direction changes gradually over distances of hundreds of light years. As interstellar visitors cross these boundaries, they experience slow changes in magnetic field strength that alter their electromagnetic properties in ways that can be measured by sensitive instruments. The way these objects serve as natural laboratories for studying the behavior of matter under conditions of perfect vacuum demonstrates their unique value for understanding fundamental physics. The interstellar environment provides a vacuum quality that cannot be achieved in any terrestrial laboratory, allowing chemical and physical processes to proceed without the interference of atmospheric molecules or surface contamination. The surfaces of these wanderers represent some of the cleanest interfaces between solid matter and empty space that exist anywhere in the universe. The gravitational wake structures these visitors create as they move through regions of enhanced dark matter density provide opportunities to study the properties of this mysterious substance through its gravitational interactions with ordinary matter. As they travel through dark matter clumps, these objects create subtle disturbances in the dark matter distribution that persist long after they've passed, generating gravitational waves so faint they're barely detectable, but carrying information about the fundamental properties of dark matter particles. The way these wanderers respond to the acoustic waves that propagate through the interstellar medium reveals the sound-conducting properties of the sparse gas that fills the spaces between stars. Shock waves from stellar explosions create pressure waves that travel through the interstellar medium at speeds determined by the temperature and density of the gas. When these acoustic disturbances encounter an interstellar visitor, they create tiny accelerations that can be detected through careful measurements of the object's motion over extended periods. The chemical evolution that occurs within the atmospheres of these objects, if they possess any residual gas envelopes, provides insights into the behavior of matter under the extreme conditions of deep space. Some interstellar visitors may retain thin atmospheres of sublimating ices or outgassing organic compounds that interact with cosmic radiation and stellar winds in ways that create unique chemistry. These processes occur so slowly that individual reactions might take decades to complete, creating chemical environments that exist nowhere else in the universe. The way these cosmic travelers interact with the streaming motions of the local standard of rest demonstrates their role as markers of the galaxy's fundamental reference frame. The local standard of rest represents the average motion of stars in our galactic neighborhood, and interstellar visitors provide independent measurements of this fundamental velocity standard. Their trajectories, unaffected by the gravitational influences that bind stars to galactic orbits, reveal the true motion of our solar system through the galactic medium. The seismic activity that occurs within these objects as they undergo thermal cycling during stellar encounters creates internal waves that propagate through their solid matrices like earthquake tremors in miniature worlds. Temperature variations cause differential expansion and contraction within their interiors, generating stress patterns that are relieved through the formation of microscopic fractures and the propagation of acoustic waves. These internal oscillations continue long after the thermal disturbance has passed, creating natural seismographs that record the mechanical response of alien materials to cosmic heating and cooling cycles. The way these visitors serve as natural particle accelerators reveals their potential for generating high-energy phenomena through purely passive interactions with their environment. As they move through regions of enhanced magnetic field strength, charged particles trapped in their vicinity can be accelerated to significant fractions of the speed of light, creating miniature versions of the acceleration processes that occur in active galactic nuclei and pulsar magnetospheres. The isotopic fractionation that occurs within these objects over millions of years of cosmic ray exposure creates chemical signatures that reveal the nuclear processes operating in the interstellar radiation environment. Different isotopes of the same element respond differently to cosmic ray bombardment, leading to gradual changes in isotopic ratios that provide natural clocks for dating the duration of interstellar exposure. These processes occur so slowly that they provide timestamps spanning geological ages, revealing the chronology of these objects' journeys across galactic distances. The way these wanderers interact with the galactic magnetic field creates induced electric fields that drive slow circulation currents within any conductive materials they contain. These currents, flowing in response to the object's motion through the magnetic field, create their own magnetic signatures that can be detected by sensitive magnetometers. The strength and pattern of these induced fields provide information about the internal structure and composition of the visitor, revealing details about its formation history and the stellar environment where it originated. The optical properties of these cosmic messengers evolve slowly as their surfaces undergo space weathering, creating spectral signatures that record their exposure history to different types of stellar radiation. High-energy photons from hot stars cause different types of surface chemistry changes than the gentle warmth of cool red dwarfs, and these differences accumulate over millions of years to create unique spectral fingerprints that reveal which types of stellar neighborhoods the visitors have encountered during their galactic travels. The way these objects interact with the cosmic neutrino flux demonstrates their potential as natural neutrino observatories spanning galactic distances. Neutrinos from stellar core collapse events, thermonuclear explosions, and other high-energy astrophysical phenomena pass through these wanderers at rates that depend on their internal density and composition. While individual neutrino interactions are extraordinarily rare, the accumulated effects over millions of years might create detectable changes in nuclear isotope ratios within their interiors. The gravitational microlensing effects created by the densest interstellar visitors provide opportunities to study the distribution of matter on scales much smaller than previously accessible through conventional astronomical techniques. When these objects pass almost directly between Earth and a background star, their gravitational fields act as natural telescopes, slightly magnifying the star's light and revealing details about stellar structure that would otherwise be impossible to observe. These events are incredibly rare, but provide unique insights into both the lensing object and the background star. The way these wanderers preserve records of the primordial magnetic fields that existed during the early phases of galactic evolution provides insights into the origin and evolution of cosmic magnetism over billions of years. Some of the magnetic field lines frozen into these objects during their formation may represent fossil remnants of the magnetic structures that existed when the galaxy was young and had a very different magnetic field configuration than it does today. The atmospheric phenomena that occur when these visitors pass through regions of enhanced gas density create temporary interactions that reveal the properties of both the object and the interstellar medium. As they move through molecular clouds or the extended atmospheres of massive stars, they may develop brief comet-like tails or experience atmospheric drag that alters their trajectories in measurable ways. These interactions provide natural experiments in aerodynamics operating under conditions that cannot be replicated in terrestrial laboratories. The way these cosmic messengers respond to the tidal forces exerted by massive stellar remnants demonstrates the subtle but measurable effects of extreme gravitational environments on solid objects. When an interstellar visitor passes relatively close to a neutron star or stellar mass black hole, the intense gravitational gradients create tidal stresses that can deform the object's shape and alter its internal structure. These deformations persist long after the encounter, creating permanent records of gravitational interactions with some of the most extreme objects in the universe. The chemical diffusion processes that occur within these wanderers over millions of years create concentration gradients that reflect the temperature and radiation history they've experienced during their interstellar journeys. Elements migrate slowly through solid matrices in response to thermal gradients and radiation damage, creating internal layering that records the changing environmental conditions encountered during different phases of their galactic travels. These chemical archaeology records provide unprecedented insights into the evolution of stellar neighborhoods over cosmic timescales. The way these visitors interact with the streaming motions of gas in galactic fountains reveals their role as tracers of the large-scale circulation patterns that transport matter between the galactic disk and halo. As hot gas rises from star-forming regions and cool gas falls back toward the galactic plane, interstellar wanderers caught in these flows serve as passive markers that reveal the three-dimensional structure and dynamics of these vast convection cells. The electromagnetic emissions produced by these objects as they interact with the interplanetary magnetic field create weak but detectable radio signals that can be monitored by sensitive arrays of radio telescopes. These signals vary in strength and polarization as the objects rotate and tumble through space, creating unique electromagnetic signatures that provide information about their shape, composition, and internal structure. The radio emissions are so faint that they require sophisticated signal processing techniques to extract from the background noise, but they offer direct measurements of properties that cannot be determined through optical observations alone. The way these wanderers serve as natural cosmic ray detectors reveals the radiation environment of interstellar space with a precision that no artificial instrument could match. High-energy particles from distant stellar explosions, pulsar winds, and galactic cosmic ray acceleration regions strike these objects continuously throughout their journeys, creating radiation damage patterns that accumulate over millions of years. The spatial distribution and energy spectrum of this damage provides a detailed map of the cosmic ray flux in different regions of the galaxy, revealing information about the sources and propagation of high-energy particles throughout galactic space. The thermal conductivity properties of these cosmic messengers change slowly as their internal structure evolves under the influence of cosmic ray bombardment and thermal cycling. These changes create temperature gradients within their interiors that affect how they respond to stellar heating during close encounters with stars. By measuring their thermal response to solar heating as they pass through our solar system, astronomers can infer details about their internal structure and thermal history that provide insights into the physical conditions that existed in their birth environments billions of years ago. The way these objects contribute to the slow mixing of isotopes throughout the galaxy demonstrates their role as agents of chemical homogenization operating over cosmic timescales. They carry samples of stellar nucleosynthesis products from the stellar systems where they form to distant regions of the galaxy, where these isotopes become incorporated into new generations of stars and planets. This process operates so slowly that it takes billions of years to produce measurable changes in galactic chemical composition, yet it represents one of the fundamental mechanisms by which the galaxy achieves chemical uniformity. The acoustic resonances that develop within these wanderers as they respond to the pressure waves propagating through the interstellar medium create standing wave patterns that depend on their size, shape, and internal structure. These resonances can be excited by shock waves from distant supernovae or by the acoustic oscillations that occur in stellar atmospheres during certain types of stellar variability. The resulting vibrations propagate through the object's interiors at the speed of sound in their constituent materials, creating natural seismological experiments that reveal details about their internal architecture. The way these visitors interact with the cosmic web of dark matter filaments that connect galaxy clusters across the universe demonstrates their potential as probes of the largest structures in existence. As they travel along these invisible highways of dark matter, their trajectories are subtly influenced by gravitational fields that extend across hundreds of millions of light years. Their paths serve as traces of this hidden cosmic architecture, revealing the skeletal framework upon which all visible matter in the universe is organized. The magnetic field measurements possible during close approaches to these objects reveal the complex electromagnetic history they've accumulated during their galactic journeys. Their magnetic properties reflect every stellar magnetic field they've encountered, every interaction with interstellar magnetic structures, and every cosmic ray bombardment event that has occurred during millions of years of travel through galactic space. These magnetic memories provide natural archives of electromagnetic conditions in stellar systems that may no longer exist, and interstellar regions that have since evolved beyond recognition. The way these cosmic travelers respond to the gentle pressure of the galactic radiation field creates slow changes in their rotation rates and orientational alignment that occur over millions of years. The combined effect of starlight from billions of distant suns creates a subtle but persistent torque that gradually alters how these objects tumble through space. This optical coupling between the visitors and the galactic radiation environment creates a kind of radiative friction that slowly synchronizes their rotation with the large-scale structure of stellar radiation fields. The crystallographic changes that occur within the mineral matrices of these wanderers provide insights into how solid materials behave under the unique conditions of interstellar space. The combination of cosmic ray damage, thermal cycling, and mechanical stress from tidal encounters creates slow modifications in crystal structure that preserve detailed records of the physical environments these objects have experienced. These changes occur so gradually that individual crystal defects might take thousands of years to migrate to their equilibrium positions, creating materials with properties that exist nowhere else in the universe. The way these objects serve as natural laboratories for studying the fundamental physics of vacuum demonstrates their unique value for understanding how matter behaves in the absence of any surrounding medium. The surfaces of interstellar visitors represent some of the most pristine vacuum-solid interfaces that exist anywhere, providing opportunities to study surface physics, quantum effects, and electromagnetic phenomena under conditions that cannot be achieved in terrestrial laboratories. As we contemplate the countless subtle processes that govern the journeys of these interstellar wanderers, we begin to understand that they represent far more than mere curiosities passing through our cosmic neighborhood. They are living libraries carrying the accumulated wisdom of millions of years spent traversing the galaxy, natural archives that preserve information about stellar systems, interstellar environments, and cosmic processes that span the entire history of galactic evolution. Their gentle presence in our solar system serves as a profound reminder that we live in a universe where patience and persistence ultimately triumph over haste and violence. These cosmic messengers demonstrate that the most significant changes in the cosmos occur not through catastrophic events, but through the accumulation of countless small, gentle processes operating over unimaginable spans of time. They embody the fundamental tranquility that underlies all cosmic evolution, showing us that the universe operates according to principles of harmony, balance, and mathematical precision. The serenity these visitors display in their unhurried passage through our solar system offers us a model for understanding our own place in the cosmic story. Just as these wanderers maintain their course with quiet confidence across galactic distances, we too can find peace in the knowledge that we are part of something far larger and more enduring than our individual lives. The same forces that guide these ancient travelers through the depths of space also connect us to every corner of the galaxy through the patient circulation of matter and energy that has been operating since the universe began. In studying these interstellar messengers, we discover that the cosmos is not a realm of chaos and conflict, but rather a symphony of interconnected processes, all working together in elegant coordination. The gentle forces that shape their million-year journeys reveal the hidden architecture of reality, from the magnetic highways that crisscross galactic space to the gravitational scaffolding that holds the universe together. They teach us that true wisdom lies not in fighting against cosmic forces, but in understanding and harmonizing with the deep rhythms that govern all existence. These wandering visitors remind us that isolation is ultimately an illusion, that every atom in our bodies has participated in the same vast recycling processes that these cosmic messengers represent. We are not separate from the universe we observe, but integral participants in its ongoing evolution, temporary arrangements of matter and energy that have achieved the remarkable capacity for consciousness and wonder. In their patient journey across the cosmos, these interstellar travelers carry not just samples of distant worlds, but also the profound message that we are all connected through the gentle currents that flow between the stars, united in the grand dance of cosmic evolution that connects every corner of the universe through the timeless rhythms of space and time. The magnetic field reversals that occasionally occur within these wandering objects create natural records of the galactic magnetic environment they've encountered across vast distances and time frames. Like cosmic tape recorders, they preserve the signatures of magnetic field changes that have swept through different regions of the galaxy over millions of years. These reversals happen so slowly that a single field flip might take millennia to complete, creating transition zones within their metallic cores that map the evolution of galactic magnetism with extraordinary precision. The way these visitors respond to the subtle gravitational waves that ripple through space-time reveals their potential as components of a galaxy-wide gravitational wave detection network. When massive black holes merge in distant galaxies, they create disturbances in the fabric of reality itself that propagate outward at the speed of light. These waves are so faint by the time they reach our cosmic neighborhood that they cause changes in distance smaller than a proton's width. Yet over the vast baselines between multiple interstellar objects, these tiny effects might become measurable with sufficiently advanced technology. The crystalline stories of formation processes that occurred under conditions, inclusions found within these cosmic wanderers, tell we can barely imagine. Some contain mineral GR, the outer layers of massive stars. Some visitors may carry within their surface layers particles that were expelled from stars during their main sequence lifetimes, preserving direct samples of stellar atmospheres from epochs when the galaxy had a very different chemical composition than it does today. These ancient stellar winds, frozen in time by the perfect preservation conditions of interstellar space, offer glimpses into stellar physics operating under primordial conditions. The acoustic properties of these wandering objects change gradually as space weathering alters their surface texture and internal structure. Micrometeorite impacts create microscopic fractures that modify how sound waves propagate through their solid matrices, while cosmic ray bombardment slowly changes their density distribution. These acoustic evolution processes occur so slowly that the objects develop unique sound signatures that encode their entire history of environmental exposure, creating natural musical instruments that have been tuning themselves for millions of years. The way these visitors interact with the galactic chemical gradient reveals their role in the slow process that distributes elements throughout our cosmic neighborhood. Our galaxy exhibits a radial gradient in heavy element abundance, with regions closer to the galactic center containing higher concentrations of metals produced by stellar nucleosynthesis. Interstellar wanderers traveling across this gradient carry chemical samples from one zone to another, contributing to the gradual mixing that operates over billions of years to homogenize the galaxy's elemental composition. The electromagnetic induction phenomena that occur within these objects as they move through regions of varying magnetic field strength create weak but detectable electrical signatures that reveal their internal conductivity structure. As they travel from regions of weak magnetic field into areas of enhanced field strength, eddy currents develop within any metallic components they contain, generating their own magnetic fields that interact with the galactic magnetic environment. These induced electromagnetic effects provide natural experiments in planetary-scale electrodynamics, operating under conditions impossible to replicate in terrestrial laboratories. The way these cosmic travelers respond to the pressure waves generated by stellar winds creates opportunities to study the fluid dynamics of rarefied gas interactions. When they encounter the termination shocks where fast stellar winds collide with the slower-moving interstellar medium, they experience brief periods of enhanced particle bombardment that alter their surface chemistry in measurable ways. These interactions occur over timescales of decades or centuries, fast enough to be potentially observable during human lifetimes, yet slow enough to reveal the gradual nature of most cosmic processes. The isotopic decay chains operating within these wanderers provide natural atomic clocks that have been running continuously for millions of years, offering unprecedented opportunities to study nuclear physics under the unique conditions of deep space. Radioactive elements trapped within their crystalline matrices decay at rates determined by fundamental nuclear constants, but the cosmic ray environment they've experienced during their journeys can sometimes alter these decay rates in subtle ways that reveal information about the high-energy particle flux in different regions of the galaxy. The way these objects serve as natural sediment traps for interstellar dust creates layered surface deposits that record the changing composition of the galactic medium they've traveled through. Different types of dust grains settle onto their surfaces at rates determined by the local dust density and the object's gravitational cross-sections. Over millions of years, these accumulating layers build up geological records that map the dust properties of every galactic region they've encountered, creating natural core samples of interstellar material spanning vast distances and time frames. The gravitational harmonics that develop between these visitors and the binary star systems they encounter demonstrate the musical mathematics underlying celestial mechanics. When an interstellar wanderer passes through a binary system, it doesn't simply follow a single curved trajectory, but instead executes a complex gravitational dance that can be described in terms of harmonic oscillations and resonant frequencies. These gravitational symphonies play out over decades or centuries, creating orbital melodies that reflect the fundamental frequencies governing cosmic motion. The way these wandering messengers interact with the galactic corona, that vast halo of hot gas that surrounds our galaxy, reveals the three-dimensional structure of one of the most mysterious components of galactic architecture. As they travel through regions where the corona density varies, they experience different levels of atmospheric drag that create measurable perturbations in their trajectories. These interactions provide natural probes of coronal structure that complement our limited observational capabilities for studying this nearly invisible component of the galactic ecosystem. The chemical weathering patterns that develop on the surfaces of these cosmic visitors create natural laboratories for studying how different materials respond to millions of years of cosmic ray bombardment. Organic compounds undergo slow polymerization reactions that create complex molecular networks unlike anything found on Earth, while metallic surfaces develop oxide layers with unique crystalline structures that form only under the pristine vacuum conditions of interstellar space. These space-weathered materials represent entirely new classes of matter with properties that challenge our understanding of solid-state physics and chemistry. The way these objects respond to the acoustic oscillations that propagate through stellar atmospheres during certain types of stellar variability provides insights into the sound-conducting properties of tenuous plasma environments. When they pass relatively close to pulsating variable stars, they experience acoustic waves transmitted through the sparse interstellar medium that create tiny but measurable accelerations. These stellar seismic signals propagate across interstellar distances at speeds determined by the temperature and ionization state of the intervening gas, revealing information about plasma physics operating on cosmic scales. The magnetic field line reconnection events that occur when these visitors cross the boundaries between different magnetic domains in galactic space create brief but intense electromagnetic phenomena that illuminate their surfaces with invisible auroras. These reconnection events release stored magnetic energy in ways that accelerate charged particles to high velocities, creating temporary radiation environments around the wandering objects that may persist for years after the initial magnetic encounter. The resulting particle bombardment creates unique chemistry on their surfaces that serves as a record of magnetic field interactions throughout their galactic journey. The way these interstellar messengers preserve information about the cosmic ray acceleration mechanisms operating in their birth stellar systems provides direct evidence of particle physics processes that occurred billions of years ago. Some cosmic rays are accelerated in supernova shockwaves, others in the magnetospheres of rapidly rotating neutron stars, and still others in the accretion disks surrounding stellar mass black holes. The radiation damage patterns accumulated in these wandering objects encode signatures of these different acceleration mechanisms, creating natural particle physics experiments that have been running continuously since before our solar system formed. The thermal conductivity gradients that develop within these visitors over millions of years of temperature cycling create internal heat flow patterns that mirror the large-scale thermal structure of the galactic disk. Regions closer to their surfaces, which experience the greatest temperature variations during stellar encounters, develop different thermal properties than their deep interiors, which remain at nearly constant temperatures determined by the cosmic microwave background radiation. These thermal stratification processes create natural models of planetary thermal evolution operating under the unique conditions of interstellar space. The way these cosmic wanderers interact with the streaming motions of gas in galactic shock fronts reveals their role as tracers of the most violent processes occurring in the interstellar medium. When massive stars explode as supernovae, they drive shock waves through the surrounding gas at velocities that can exceed 1,000 kilometers per second. Interstellar visitors caught in these blast waves experience brief periods of intense heating and acceleration that leave permanent signatures in their surface composition and internal structure, creating natural records of stellar death events that occurred millions of years ago in distant parts of the galaxy. The crystallographic memory effects that occur within the mineral grains of these objects provide natural archives of the pressure and temperature conditions that existed during their formation epochs. Different crystal structures are stable under different environmental conditions, and the mineral assemblages found within these wanderers reflect the thermodynamic equilibria that existed in their birth nebulae billions of years ago. Some crystals preserve evidence of formation in the high-pressure environments near massive stars, while others record condensation from low-density gas clouds in the outer regions of stellar systems. The way these visitors respond to the tidal forces exerted by encounters with rogue planets demonstrates the subtle but measurable effects of planetary mass objects drifting through interstellar space. When an interstellar wanderer passes close to a free-floating planet that has been ejected from its birth stellar system, the gravitational interaction creates tidal stresses that can alter the visitor's shape and rotation state. These encounters are incredibly rare, but leave permanent signatures that provide evidence for the population of rogue planets that may significantly outnumber the planets bound to stellar systems. The electromagnetic phenomena that occur when these objects pass through the heliopause, the boundary where the solar wind meets the interstellar medium, create natural experiments in plasma physics that reveal the properties of both environments. As they transition from the solar-dominated space within our heliosphere to the truly interstellar medium beyond, They experience changes in the charged particle environment that alter their surface electrical properties and create detectable variations in their radio emissions. These boundary crossings provide direct measurements of the interface between stellar and interstellar environments. The way these cosmic messengers preserve records of the galactic chemical evolution over billions of years demonstrates their value as time capsules from epochs when the universe had very different properties than it does today. Elements heavier than hydrogen and helium have been gradually accumulating in the galaxy through successive generations of stellar nucleosynthesis, and the chemical composition of these wandering visitors reflects the metallicity that existed in their birth environments. Some may carry samples of nearly pristine primordial material from the epoch when the galaxy contained almost no heavy elements, while others preserve evidence of the chemical enrichment that occurred as massive stars lived and died. As we reach the end of our peaceful journey through the cosmos, we find ourselves forever changed by these gentle messengers from beyond our solar system. These interstellar wanderers have shown us that the universe operates not through chaos and violence, but through patience, persistence, and the quiet accumulation of countless small processes over unimaginable spans of time. In their unhurried passage through our cosmic neighborhood, they remind us that we are not isolated inhabitants of a single star system, but citizens of a vast galactic community where matter, energy, and wonder flow freely between the stars. Tonight, as you drift towards sleep, remember that you too are part of this cosmic dance, connected to every corner of the galaxy through the same gentle currents that guide these ancient travelers on their million-year journeys through the serene depths of space.